Welcome back to the deep dive. Today we are going to start with a very specific, maybe slightly stressful memory that I think a lot of our listeners will recognize immediately.
Oh, I love a good trip down memory lane. Where are we going today?
We are going back to the chemistry lab,
Mm.
class 12. You know the vibe, right? The smell of faint sulfur in the air, the clinking of glassware, the pressure of the practical exam.
I can feel it.
So you're running an experiment to check the freezing point of a solution. You've done the prep work perfectly. You've dissolved common salt sodium chloride in water. You've done the theoretical math based on the formula you learned in class. And, for a fact that the freezing point should drop by exactly 1.86 degrees Celsius.
Okay, I am there. I have my lab coat on. I'm feeling confident.
Exactly. You put the thermometer in, you wait for it to settle, you squint at the reading, and your heart just stops. It reads minus 3.72 degrees Celsius.
Wow.
That is almost double the expected drop.
I can feel the panic rising just hearing that. That is the moment you start tapping the thermometer. No.
Yeah.
You're thinking, is this thing broken? Did I weigh the salt wrong?
Did I have to restart the whole experiment with 10 minutes left? It's the universal student nightmare.
It really is.
But here is the twist, and this is what we are unpacking today. What if I told you that your equipment is absolutely fine? You did not make a mistake. The solution is actually behaving exactly as it should. The math you did on paper was just, well, incomplete.
That is a great setup because today we're not just talking about a lab error. We are doing a deep dive into abnormal molar masses from Unit 1 solutions.
Right.
And I want to set the context early here. This isn't just about passing an exam question. This concept is the fundamental key to understanding the actual state of a substance when it enters a solution.
Right, because when we look at a bottle of salt or acid, it's just a solid or liquid. But once it hits water, it changes its entire character.
Completely. It's like a secret life of molecules. Does the substance stay together? Does it break apart into pieces? Does it clump up with its neighbors? If you don't understand abnormal molar mass, you are basically flying blind. You can't interpret any data from colligative properties correctly.
It's the difference between textbook theory and the real world.
Precisely.
So let's peel this back layer by layer. At the simplest level, the level we all learn first, we are used to calculating molar mass by just looking at the periodic table, simple addition.
Sure. Sodium is 23, chlorine is 35.5. Add them up, you get 58.5 grams per mole. That is the label on the bottle. That is the theoretical value.
But in this unit's solutions, we learn that we can also measure molar mass indirectly. We use these things called colligative properties.
Like freezing point depression.
Exactly, like how much the freezing point goes down to sort of reverse engineer the mass of the solute.
And that's a standard technique. And usually those two numbers, the one from the periodic table and the one from the experiment, they match perfectly. If you do this with sugar or glucose, they line up.
But then you have these rebel substances. And sometimes you get a number from your experiment that is wildly different from the periodic table. It's abnormal.
And this is where students get so tripped up. I saw a note in our source material calling this the misunderstanding trigger. Students immediately assume their experiment failed.
I did something wrong.
That's the biggest hurdle, yes. They think, oh, my calculation is wrong because the mass is abnormal. We need to flip that thinking. The measurement is actually correct for the number of particles present in that beaker.
So the thermometer isn't broken?
The thermometer isn't broken. The experiment is telling you the truth. It's just counting what's actually there, even if that doesn't match the label on the bottle.
So why the discrepancy then? What is happening in that beaker to mess up the count?
It comes down to two processes, dissociation and association. The solute particles are either, splitting apart or they're sticking together.
Okay, let's visualize this. I want to run a mental movie for everyone listening. Let's take that salt example from the intro.
Okay, everyone close your eyes. Picture you're holding 1 mole of NaCl crystals. It's about 58 grams, a nice little pile of white salt. You assume you're holding 1 mole of particles.
1 mole of things.
Yes. Now dump it into water. In your mind's eye, see the water molecules attacking that crystal structure, the ionic bonds. They just snap.
It's pretty violent down there at the molecular level, isn't it?
It is. The water surrounds the ions. Suddenly, that single unit of NaCl splits. It becomes 1 sodium ion floating off to the left and 1 chloride ion floating off to the right.
So physically, you put in one thing, but now there are 2 things swimming around.
Precisely. If you started with 1 mole of salt, you now have 2 moles of independent particles.
Okay, and this connects to the core mechanism of colligative properties. I like to think of these properties like freezing point depression as a kind of blind turnstile, a blind counter.
That is the perfect analogy. Imagine a turnstile at a stadium entrance. It clicks every time something passes through. It
Hmm.
doesn't have a camera. It doesn't check ID cards. It doesn't care if the person walking through is a giant wrestler or a small child.
It just counts one, click.
It just counts. So colligative properties depend only on the number of solute particles.
Only the number, not the identity, not the size.
Nothing else. Just the count. So go back to the salt. You put in one molecule, but it splits into two ions. The turnstile clicks twice.
And that explains our intro. The freezing point drops twice as much because the water thinks there is twice as much stuff dissolved in it.
You nailed it.
Yeah.
And because the freezing point depression is doubled, if you use that number to calculate the molar mass, the mass tells you the mass is half of what it should be. The more particles you have, the lighter each particle appears to be in the calculation.
That is actually quite intuitive once you see it. Dissociation means more particles, which means a lower calculated mass. Now, what about the opposite? What if the turnstile clicks less often than we expect?
That is association. And this happens with substances like acetic acid or benzoic acid, especially when you dissolve them in solvents like benzene.
Okay, run the mental movie for this one too.
Right, so visualize these acetic acid molecules floating around. They have these hydrogen atoms that are just looking for a connection. When two molecules bump into each other, they grab onto one another, they form hydrogen bonds, they pair up into what we call a dimer.
It's like the buddy system at school.
Exactly. Two molecules become one single unit. So you might put in, say, 100 molecules, but they pair up, and now there are only 50 particles swimming around.
So the blind turnstile only clicks 50 times.
Correct. The effect on the freezing point is cut in half. And because the effect is smaller, the calculated molar mass comes out looking huge, abnormally high.
Okay, to really cement this, I want to bring in that analogy from our notes, the conference analogy. I think this helps explain the math part so nicely.
This is one of my favorites. Let's imagine we are organizing a massive chemistry conference. We have booked a venue, ordered lunch. We expect exactly 100 attendees.
Okay, so the attendees are the molecules.
And the cost represents the molar mass.
Got it. I'm at the registration desk. I've got my clipboard.
Scenario 1, dissociation. This is our salt solution. We expect 100 people. But as soon as they walk through the door, every single person splits into two distinct personalities, maybe a professional self and a personal self. Both of them grab a separate name tag.
Oh, that's a nightmare for catering. Now I'm counting 200 name tags instead of 100.
Right. But remember, the total weight of all the people, it hasn't changed. But if you try to calculate the cost per person based on the tag count.
It looks cheaper. The cost per head just dropped by half.
Exactly. That's why dissociation leads to a lower abnormal molar mass. The cost per particle drops. Now flip it. Scenario 2, association.
Okay.
You expect 100 attendees. But this time, everyone arrives as a couple. And they refuse to take separate tags. They squeeze into a single name tag.
So now I look at my list and I've only handed out 50 tags.
But the total bill for the venue is the same. So when you calculate the cost per tag,
it skyrockets. The cost per unit is double what I budgeted for.
that is association. Fewer particles, or fewer tags, means a higher perceived molar mass.
That makes the math feel a lot less abstract. But let's step back a second. Why does this concept even exist? Why did chemists need to invent this abnormal label? It sounds like they were just trying to patch a hole in a theory that didn't work.
You know, that's actually a pretty accurate way to look at it historically. It wasn't about complicating things. It was about solving a mystery that was breaking 19th century chemistry.
Really?
Oh yes, scientists like Raoult had these beautiful laws that worked perfectly for sugar and urea. But every time they tested salts ionic compounds, the laws broke. The numbers were just way off.
They must have thought their equipment was broken, just like our student in the intro.
They did. They were completely baffled. Without the concept of dissociation, we actually cannot explain why salt solutions have such a massive impact compared to sugar. A mole of sugar in water stays as a mole of sugar.
It's stable.
It doesn't split, doesn't conduct electricity.
Yeah.
Well, it's boring in that sense. But salt is dynamic. And this discrepancy led the famous scientist Van Hoff to introduce the I factor, the Van Hoff factor, to correct the math.
And he won a Nobel Prize for that, didn't he?
The very first one in chemistry. He basically said, the theory isn't wrong, we just need to account for the actual number of particles.
We're going to get to the I factor and the exams in a moment, but first, why does this matter outside the lab? Is this just theoretical gymnastics, or does it have a pulse in the real world?
Oh, it has a pulse. Quite literally. Let's look at the tech application from our deep dive stack, the IV drip. You've seen those saline bags in hospitals, right?
Yeah, isotonic saline, usually labeled 0.9% ACL. It's the standard stuff they hook you up to if you're dehydrated.
This is life-critical chemistry. Doctors and pharmacists must match the osmotic pressure of that solution to the osmotic pressure of your blood cells. If they get it wrong,
Yeah.
the consequences are horrific.
What happens if they mess up the calculation?
If the solution is too concentrated, water gets sucked out of your red blood cells and they shrivel up. If it's too dilute, water rushes into the cells and they can swell and burst.
That's terrifying.
It is. So now think about the math. If a pharmacist calculated the concentration based on the dry powder formula mass of NaCl, assuming it stays as one particle.
They would assume 1 mole of salt provides 1 mole of osmotic pressure.
Right. But we know it dissociates, it splits into two. So the actual osmotic pressure is double what a simple calculation suggests. If they didn't account for this dissociation, this abnormal behavior, they would be creating a solution that could seriously harm the patient.
Wow, so the I factor is not just a variable on a board exam, it's a safety correction factor in medicine.
Absolutely. It proves that abnormal molar mass calculations aren't just textbook theory. They map to how biology actually functions.
I have another scenario here from the notes that I found really interesting, a counterintuitive example. It says, you might think measuring the molar mass of an unknown salt would give you the formula mass.
Yeah, this is a fun thought experiment. Imagine you are in the lab. You have an unknown salt. You want to find its formula mass. So you dissolve it, you measure the freezing point depression, and you run the standard calculation.
Seems logical. That's how we find the mass of unknown compounds.
But if this unknown substance is an electrolyte, let's say something like calcium chloride, calculus runner, it splits into 3 particles.
Oh, right. 1 calcium ion and 2 chloride ions.
The turnstile clicks 3 times for every 1 unit.
So your calculated molar mass will be
1/3 of the actual mass. You might think, wow, I've discovered this tiny light molecule. But in reality, you have a heavy molecule that just broke into 3 pieces.
It's like buying a heavy bag of apples, but when you look inside, you see it's all slices, so you assume you bought something else entirely.
That is a great way to put it. You have to know the apples were sliced to understand the weight.
Okay, we've covered the concepts, the analogies, the history, and the life or death stakes. Now, let's pivot to the listener who's sitting there with a pen and paper, getting ready for the board exams. We have a list of exam-safe clarity lines. These are the golden rules.
These are the distinctions that get you full marks. If you're writing a descriptive answer or solving a numerical, this is your checklist.
Let's run through them. Rule number 1.
Rule 1, the definition. Always start here. Abnormal molar mass occurs when the actual number of particles in solution differs from the number of formula units you added. Don't overcomplicate it. It's just a counting problem.
Simple. Rule number 2.
Rule 2, the correction. The Van Hoff factor, I, is the magic number. Your formula for any colligative property, whether it's freezing point, boiling point, or osmotic pressure, must be modified. You have to write delta T equals I times K times M.
Do not forget the I. I feel like that is where 50% of marks are lost. Students just memorize the standard formula and forget to add I for electrolytes.
It happens all the time. For sugar, it's 1, so it doesn't matter. But for NaCl, I is 2. For MgCl, I is 3. That little letter changes the entire answer.
Okay, rule number 3. This one is about the direction of the error.
Rule 3, dissociation. Dissociation creates more particles. More particles means the measured molar mass will be lower than the theoretical mass. Just think. Salt splits, mass drops.
And the inverse for rule 4.
Rule 4, association. Association results in fewer particles. Fewer particles means the measured molar mass will be higher than the theoretical mass. Think. Acid pairs up, mass goes up.
And finally, rule 5. This is about the strength of the electrolyte.
Rule 5, the range of I. You need to distinguish your electrolytes. For strong electrolytes like strong salts, we assume they fully dissociate. So I is just equal to the number of ions. For NaCl, I is 2.
But what if it's a weak electrolyte, like a weak acid?
That's where it gets tricky. Weak electrolytes only partially dissociate. Maybe only 10% of the molecules split. So I will be a decimal number somewhere between 1 and the max number of ions.
So I might be 1.05 or 1.2. Not a clean integer.
Exactly. And you often have to calculate it using the degree of dissociation, which is alpha. That is usually the hardest type of numerical problem you'll face.
Okay, before we wrap up, let's do a quick recap. If you, the listener, Take away 3 things from this deep dive. What should they be?
First, the core mechanism. Colligative properties are blind counters. They count particles, not what the particles are. One ion is one click.
Second, the analogy. Remember the conference. If attendees split into 2 personalities, dissociation, the cost per head drops. If they couple up association, the cost per head rises.
And third, the application. Never forget the IV bag. Our medical understanding of hydration depends entirely on knowing that salt splits in 2.
And the action item for your exams, whenever you see a solute in a problem, just pause. Ask yourself, is this an electrolyte? Does it split? Does it associate? If the answer is yes, you must use the Van Hoff factor I.
And if I can leave our listeners with one final thought, we've spent this whole time calling this abnormal molar mass. It sounds like a mistake, no, like something went wrong.
It does sound negative, doesn't it? Like a bug in the system.
Exactly. But actually, I think we should view it differently. If measuring the freezing point gives us this wrong or abnormal molar mass, we can reverse the math. We can use that discrepancy to figure out exactly what is happening inside the solution.
What do you mean by that?
Well, by comparing the theoretical mass to the measured abnormal mass, chemists can calculate the exact degree of dissociation. We can figure out, oh, this weak acid is 15% dissociated in this solvent.
So it turns a problem into a probe.
Precisely. It turns this annoyance into a powerful detective tool. It allows us to see into the molecular world and measure how strong bonds are or how a substance interacts with a solvent. It's not a bug in the system. It's a feature that reveals the inner life of the solution.
That is a much better way to frame it. It's not abnormal, it's revealing.
Revealing molar mass. I like that. Maybe we should petition to change the textbook terminology.
We will start the petition right after this. Well, that is it for our deep dive into abnormal molar masses. Don't be afraid of the I factor when you see those numericals. You've got this.
Keep questioning and keep connecting the dots.
See you in the next deep dive.